Hello and welcome to the Graph AI channel. This channel documents our research into the behavior of AI agents, or creatures, living on graphs. This research stems from older ideas, which we may cover in the future. The historical working code name for these ideas has been CORGAN, short for Competitive Organisms on Networks. The specific project we'll showcase in this episode combines two recent advances in AI research, a strategy algorithm, like AlphaZero, and graph neural networks. AlphaZero, descended from the earlier AlphaGo, was developed by the British AI company DeepMind. AlphaGo gained attention in 2016, when it beat a human champion in the game of Go. Graph neural networks, or GNNs, apply AI to graphs, the subject of a branch of math, called graph theory. We can ask if the concepts researched here have parallels in nature. The most obvious thing that comes to mind is a spider on a spider web. However, it's not a good example. A spider web can be seen as a graph, but spiders are usually bigger than most of the graph's edges. Because of this, and because spider webs have dense coverage, the spider's motion is not confined by the graph edges. Spiders can move freely across the whole web, as if it were one big flat surface. An ant farm is a better analogy, especially of the narrow flat kind, with corridors rather than chambers. Competitive behavior requires a test case to demonstrate results, a game if you will. The following concept was developed for this purpose. We'll call it Ringo for short. Two creatures, or bots, appear on this ring-shaped graph in separate start nodes. They travel along the edges of the graph, visiting good nodes, shown in green, avoiding bad nodes, shown in red, while trying to get to the end node. Stepping into the end node ends the game. All these special nodes are chosen randomly. Again, all this takes place on a graph. This is in contrast to virtually all games AlphaZero has tackled so far, which take place on a square grid. The rules of Ringo went through many changes, regarding how the good and bad nodes contribute to the score, how the bots see the graph, how the winner is decided, etc. In its final version, the rules are as follows. Visiting a good node gives points, but only to the first visitor. Bad nodes subtract points. The bots can see the important nodes. The bots know each other's position. The bots have access to each other's knowledge. Stepping into the end node ends the game. Once the game ends, points scored by one bot are compared to the sum of the opponent's score and points left on the board. The bot with the higher ratio wins. Following development and training, the next step was to visualize a game in 3D. But not all games are equally interesting. So AI was made to play a few dozen games, which were later played back and evaluated. The most interesting ones were passed on to the 3D engine. The 3D setting chosen for this video is a prison lake concrete maze in some faraway desert. The bots are alien creatures, one blue, called Payus, one black, called Hork. They're placed in this maze and they try to win according to the aforementioned rules. We'll now explain a few graphic elements. They don't influence the game, they're just visual aids for viewers. The good and bad nodes are shown as round enclosures with colored discs. The rings they emit are for better visibility by viewers, though they can be thought of as a signal the bots can detect. When the bots get near these nodes, the rings disappear. In the distant view the bots are small, so their locations are highlighted by blue and black rings. These trails show the paths taken by the bots. The end node is the structure that looks like a Greek temple with a rotating light. For each bot, its instrument panel shows its POV, and a local map of the graph with the travel direction pointing up. On the right we see numerical data. The distance traveled so far. Actions taken by GNN's search tree of possibilities. Edge values as computed by the GNN. And edge values suggested by spatial relationships. In some close-up views, these values are shown as bars mapped onto corresponding pathways. This graph above shows how likely the bot thinks he is to win as the game progresses. This is the current point score of the bot. But remember, it's not the raw point score that wins the game, but rather the ratio between points scored and the total points in the game. This bar shows the corresponding ratio. We'll now show two sample games, using the two most successful models. The first model uses priors. This means that the bots are presented with info on which edges are promising in terms of spatial location. This is a suggestion, not a command. The bots can use this info to make their own decision. Here are the training graphs for this model. There is a big drop-off in learning time, after 50 or so iterations. The learning rate, measured in games played against itself, is moderate. And now a sample game in 3D using this model. And off they go. The bots are heading for the green nodes. The blue Payus is optimistic about the game, the black Hork is pessimistic. Payus now has enough points to win, so he's heading for the exit. Payus now just a short distance from the goal. Payus wins. The second model doesn't use priors. In this model, a bot can visit a graph edge only once. This was done to completely eliminate the issue of flip-flopping. It occurs when a bot paces back and forth between two nodes a few times, unable to make a decision. Here are the training graphs for the second model. The iteration times are more even, and the learning rate is high from the beginning. Now an example game in 3D. An interesting beginning, both bots decide to walk along the perimeter. They're going for the green nodes. Looks like Hork thinks Payus will get to the one at the edge faster, so he aims for the other one. They now both have enough points to win if they reach the green node near the goal, so they're headed there. Payus snatches one more point before reaching the goal. Payus wins again. Thanks for watching. A question to ponder: do these bots know they live in a simulation?